Hey, welcome, guys. I'm here to talk about sustainable brewing with mash filtration. I'm Rich Michaels. I'm with IDD Process and Packaging. My background is in brewing for the last 30 years. Kind of start this out, unfortunately, I know it's right after lunch for some of us, and we're going to be doing a little bit of math lesson to figure out where we're at right now as far as brewing efficiency. So with that, I'll get started. Okay, so what is our job as a brewer? We spend most of our time cleaning. Without sanitation practices, quality is going to fail in the brewery. Um, and our job is to brew and sell great beer. There are many successful business models: brew pubs, tap rooms, production breweries. A lot of this applies to everybody here today. Number three, we need to run a successful business. This is not a hobby and should not be treated as such. And this is where sustainability comes in. So brewing beer, we make wort. Yeast is actually what makes the beer. Our job is to extract sugar from the grains to produce wort. We add hops to add flavor and aroma to the beer. As we're still learning, in many cases, we're adding precursors that the yeast will help us release to become finished beer. Yeast job is going to be to ferment sugars, produce alcohol and esters. The hops will provide bitterness and aroma to the beer. Yeast can also change some of those hop contributions to unique flavors, such as glycols, thiols, and good things like that. So our key to success in the brew house, we need to produce a consistent wort, make a consistent product, keep our yeast happy, healthy, and clean to produce a great tasting product. And as brewers, we should be benchmarking ourselves for sustainability and quality. So how do we brew house? We look at things in the brew house. We look at quality. We're hopefully going to achieve relationships and supply chains that give us consistent materials. As brewers, we want to have a consistent process that includes timing, pH, gravities, and ideally consistent flavor in our beer. Notice the consistency is our trend here. So what do we want to look at in a brewery efficiency-wise? How many hours does it take to complete a brew? How much labor does it cost to produce a batch of beer? That comes down to time and wages. We want to have consistent recovery of extract. We want to get the same amount of sugar out of the beer each time. Obviously, our goal is to do as much as possible. And this can be done with a combination of measurements and calculations. And we're going to talk about those calculations today. Then we'll talk about different brew houses and what they can bring to that for us. So brewing efficiency can be calculated by dividing the amount of sugar that's potentially available. How good of a job do we get sugar out of the grain? The amount of sugar extracted that's available, that's our potential extract. And we'll take a look at our malt analysis to figure that out. For example, if we have 80 pounds of potential extract, we extracted 60 pounds of that sugar, our efficiency would be 75%. It's important to note that efficiency can vary from batch to batch. It's important to measure it for each batch you make. This will allow you to make adjustments to your process to make sure you get consistent results every time. So how often should we do this? Ideally, every time. Like I said, this number can vary based on the equipment design, the grist load, the recipe, the process, and yes, the brewer. Some people do things differently than others, and that can result in efficiency changes. This is also a great technique to evaluate process and raw materials changes. From year to year, grain can vary. We've all struggled with some of the recent years' malts at one point or another. This is a way to note that change and see what it really costs you. So you're going to do a simple brew with 500 pounds of good quality two-row malt, and you have a malt analysis. You guys always ask for malt analysis, right? It's going to read something like this. This was broken in half in the center here. We'll have a lot number. We'll have moisture, extract, fine grind, extract coarse, color. We're going to start to look at enzyme levels and things like that. For us right now, the important number here is extract coarse grind as is. This is expressed as a percentage. For example, this sample here, the analysis is 77%. That means for 100 pounds of grain, there's potentially 77 pounds of extract available to us as brewers. So to figure out how much total extract is available, we take our 500 pounds, multiply that by our 77% extract, and we determine that there's 385 pounds of potential sugar that we could recover to our wort. So put that number aside for now. We'll get back to that. So we do our brew, and we find out our measured yield is 8 barrels of beer, or 8 barrels of wort to the fermenter at 13 degrees Plato. For those using specific gravity, that's 1.0526. So we can look this up on an extract table, and we can determine that 13 Plato wort contains 35.29 pounds of extract per barrel. So 8 barrels times 35.29 pounds is equal to 282 pounds of extract. 282 divided by the amount of potential that we had, we can determine that our efficiency is 73.3%. This is pretty normal for a craft brewery. I've seen numbers as low as 60%. I've seen numbers approaching 90% and a bit higher with some equipment. In this example, 26.7% of the sugar that we could have made beer out of did not make it into the batch. It means we're feeding cows. So to get our available extract, we multiply our pounds of malt times the lot analysis number for extract coarse grind as is. And that gives us our potential available extract. For example, if we have grain that's 77.2% extract coarse grind as is, and 1,000 pounds of that grain, we have 772 pounds of potential extract available. Now we can convert Plato in our kettle or fermenter. We can convert that from pounds of extract, from Plato to pounds of extract per barrel. The formula is 259 plus our degrees Plato times our degrees Plato divided by 100. So the example here is we'll take 15 degrees Plato. We'll convert that. So 259 plus 15 times 15 divided by 100 equals 41.1 pounds of extract per barrel. That's kind of an approximation. That's from an old technical brewer's book called The Practical Brewer. And the value for 259, that actually comes from the weight of water. And it's actually a rounded number. The number is actually 258.7 pounds. For best results, you should probably use the ASPC extract table. That's what those are for. And to figure out our pounds of extract recovered, we take our pounds of extract per barrel times the number of barrels we have, and that gives us our number of extract that we actually recovered. So what does that mean? So if we took 100 pounds of grain at 75.8% extract, and we are 65% efficient in our process, we're going to recover 49.3 pounds of extract. So of that 100 pounds of grain, about half of that will become beer, and the rest of it goes on to feed the animals. And that's non-recoverable things such as protein, fiber, moisture. And you can see as that goes up, 80% efficient, we recover 60 pounds of extract. At 95 efficiency, we recover 72 of 75.8% extract. So we'll just take a look at extract here. This kind of breaks down a little bit simpler. This takes out the things that we're not really interested in, such as protein, fiber, and moisture. And here's what it comes out to be. We're losing 35% of our potential extract, 20% of our potential extract, or 5% for 65% efficiency, 80% efficiency, and 95% efficiency. I don't think anybody here would be happy losing 35% of their cans, cardboard, or labels, but yet some people are losing this much extract from their grain on a regular basis. So we'll talk about mash filters. Mash filters is a technology that goes back more than 100 years. 35% of the world's beer is currently made on a mash filter. The filtration process has been updated through the years, and as raw material costs rise, this technology makes sense on a smaller scale. So what is a mash filter? It's a multiple frame filter with alternating recessed chambers that hold the mash. Basically, it's a big strainer. Diffusing chambers contain bladders that allow us to recover extract by squeezing the grain to recover the wort from the trapped grain. Mash is pumped into the filter chambers, which retain the grain. Wort continues on to the brewing process. Sparge water is used to push the wort out and rinse the grain. And then the plates are inflated with water or air, squeeze out liquid through the filter cloths. This leaves fairly dry spent grain. So basically think of it as a small series of vertical lauter tons with a short pathway through the grain. So worldwide, where are they used? Coors, Bass, Carlsberg, Heineken, Guinness, Chimay, some larger craft breweries, Full Sail, Alaskan, Crux Fermentation in Oregon, Calvert Brewing in Maryland, and actually Pabst in Milwaukee was a mash filter system before they closed up a few years back. I work out of New York. We have some other larger craft breweries, Genesee Brewing Company, Matt Brewing Company, both have 500-barrel mash filter systems. Frog Alley, where I used to work, Good Nature, Roaring 20s, Industrial Arts. So there are quite a few of these around. These are just kind of a handful of them I know off the top of my head. So how does it work? We'll take a look at Darcy's Law. This describes how liquid flows through a porous medium. It was from a French engineer in the 1850s, measuring how water flowed through sand. In this case, we're going to be looking at how wort flows through grain and water flows through grain. I won't get into the details of the formula, but basically, if we can interpret this, bigger numbers on top and smaller numbers at the bottom, increase our flow rate and extraction. So we can increase V, our flow rate. We're going to increase our surface area. We can increase our pressure differential. We'll decrease our viscosity and decrease the length of our bed. We'll talk about that in a second. So the mash filter has advantages over a lauter tun. We have greater surface area. We have higher pressure differential. In a lauter tun, we separate and flow based on gravity. With a mash filter, we can actually pump and control the pressure. We typically go through a stepped mash where we have higher temperature and lower viscosity. That helps things run off better. And bed depth. Between these plates, there's chambers that are 2 to 3 inches across. We only have to flow through 2 or 3 inches of grain. As where with a lauter tun, you might see 16 to 24 inches of grain. Like I said, bigger numbers on top and smaller numbers on the bottom, increased flow and extraction. An example is a 20 hectoliter mash filter that I've worked with at IDD. Has a surface area of 23.6 square meters and a bed depth of 2 to 5 centimeters. So what that means is the equivalent lauter tun would be more than 18 feet in diameter for a 20 hectoliter or 17 barrel system. Much larger surface area, much faster flow as well. So how it works, we looked at there's a couple of mash filters on the left here. If you're to take a cutaway view of them, you can see here there's space between those plates. We pump mash in. Typically, we fill the entire thing up, displacing any air out of the system. The mash continues to pump through. The grain material, the husk material, is all caught between the plates. Clear wort continues to flow on out through the plates and is collected off the end manifold. When we're out of mash to pump through, we pump water behind that, and that flushes the wort out of the chambers, rinses the sugars in the grain, sparging, just like we do with lauter tun. And at the end, we can actually inflate bladders every other plate, squeeze that mash, recover that liquid, and recover that extract. What that means is, with a typical mash filter without a bladder, you'll see recovery rates between 88 and 92%. And with the bladder, you typically see recovery rates upwards of 95%. At the end, after the bladder squeezes the spent grain, You actually recover most of the liquid out of it. They're about 70% solids here. These are pictures of spent grain right out of the mash filter. And the top left photo here, you can see the operator is actually scraping that mash out of the system. It actually comes out pretty easy. Just basically touch it and it falls off as a single sheet. And often you typically recover the spent grain to a conveyor that carries it to a bin at the end of the system. Other advantages, other than the extract recovery, we have a much lower use of water. Traditional brewing in a small lauter tun system, it's not uncommon to see water use rates upwards of 7 barrels of water to produce 1 barrel of finished beer. The mash filter can greatly reduce water usage. Numbers are often as low as 3 barrels. Example here, Alaskan Brewing Company did a full brewery audit. They reported 3.6 barrels of water used to produce 1 barrel of beer. Their spent grain is so dry that they can actually blend it and use it to fire their boiler. Historically, they had to ship their spent grain to the lower 48 states at a pretty significant cost. And now they can actually use it as a fuel source and not have to ship it. Spent grain now produces about 50% of their steam. They can't run that stuff completely by itself. The moisture content is still a little bit high to burn, so they do blend it with wood chips and wood sawdust, basically. They can actually blend the moisture content low enough with that and fire the boiler with that. And water usage is another important parameter to benchmark in your brewery. Water is a limited resource. Water is not terribly expensive, depending where you're in the country. There's a significant cost to get rid of it and sewer charges and things like that. So if you can reduce the amount of water you're wasting, it's definitely beneficial to the bottom line. Speed on a mash filter. Typically, you can start a new brew every 2 hours. Things go through the system quite quickly. Typically, in my experience, the past couple of years, we've been running 3 brews in just over 8 hours, start to finish. The fastest turns I've seen in breweries that I visited recently were 14 brews in 24 hours. And typical extraction efficiencies are 95% plus. Obviously, the reduced malt usage is a significant cost savings, significant savings in water as well. And as breweries, we've got a lot of small breweries that are remote that may not be on municipal wastewater systems. If they have to process their own wastewater, if you can reduce the BOD and the amount of water on that system, that's definitely a benefit to the brewery. So compare lauter tun versus mash filter. Typical lauter tun, you'll see 4 to 8 brews per 24 hours. Mash filters, 12 to 14 brews for 24 hours. Flow through the mash filter with the mash is typically 15 to 30 minutes, depending on what you're making. Sparge is pretty quick after that, so you can definitely do a lot of turns. Comparison again, thick bed, lauter tuns typically run a bed depth of 16 to 24 inches, depending on the design. That may be as low as 12 inches. Mash filters, thin bed, typically 2 to 3 inches bed depth, so you get better flow there. Lauter tuns, 60 to 85% extract recovery, I find to be typical. Combination mash lauter tuns tend to be on the low end of that. They're typical in a lot of small breweries. Mash filter, 95+%. Lauter tun has a little advantage here, flexible loading and performance. You can actually run that lauter tun, with a bed depth between probably 12 and 30 inches. You're going to get a pretty big variation in performance there, but it will work. Mash filter, you do need to fully load to make things work. There's ways to deal with that. You can actually take the end plate, lift it up, and drop it in the middle of the deck and decrease the size of the mash filter. Optimal loading on a mash filter is about 40 pounds per cubic foot. That's kind of how we look at it. You look at optimal loading on a lauter tun based on how many kilograms per square meter. Grist, typically in a lauter tun, we want a fairly coarse grist. We tend to wind up with slow conversion. We see conversion, half hour, 40 minutes, probably a full 60-minute mash cycle. You see quite a bit shorter cycle on the mash filter. I know some breweries that have switched from lauter tons to mash filters have found that to be a challenge. They're surprised that you'll see conversion typically in 5 to 10 minutes. So it's important that you get your strike water temperature correct. Things are happening pretty quickly with the fine grist. Water usage, another huge advantage to the mash filter. Typically see about half the water usage. With the mash filter, it's really important to have a temperature-controlled mash to get things to run nicely. You have to be able to pump that mash through the filter. A combination mash water ton, that's not necessary. But you may have step control if you have a separate mash vessel as well. If you're using unusual ingredients, such as lots of wheat, things like that, lots of flakes, you may consider using rice hulls with lauter ton. Mash filter, that's not a problem. You don't need husk material, so no need for rice hulls. There's some pretty interesting tricks you can do with the mash filter. You can do high adjunct brewing. You can use up to 100% unmalted grain. I'll talk about that in a minute. There's also some advantages without the husk. There's some other grains that you can use. We have available to us locally here in New York. Farmers growing hull-less barley. That is about 85% extract. You can definitely squeeze more beer out of that. Like I said, you can use unusual adjunct, no problem. We're doing some work right now working with unmalted barley, pretty successfully actually. You can also do unusual mash bills. I've done 75% rye beer with a mash filter. No husk, no problem. Runs just fine. A little slower on that brew, but it wasn't a big challenge. No rice hulls necessary. Efficiency, reduced labor costs with a properly sized system. You have to make sure that if you're going to be pushing your mash through a mash filter in half an hour, you need to make sure that your kettle is open and ready to take that brew. So there might be some sizing issues if you try to retrofit this into an existing system. Another cool thing you can do with these is do a filtered whiskey wash. You can actually strain the husk material out and do a filtered or lautered type whiskey wash pretty quickly with this, very efficiently. I mentioned the 100% adjunct beer. I've got a client I'm working with right now who's producing what they want to be a very green beer. It's a Kolsch style ale. We're producing it on a mash filter. It is brewed with 100% unmalted barley and local New York hops. We're using hammer mill on this because of the high moisture content of the raw barley. The raw barley is about 11 to 13% moisture. So we hammer mill it because going through a roller mill, it gets kind of gummy. But it's got about a 70% cost savings on grain and about a 60% reduction in carbon footprint. And we've done 3 full-scale test brews. This product will be going to market this month, actually. It's currently brewed on an IDD mash filter, and we've determined, after adding things up and working with some suppliers, we figured out we're saving about 2.5 kilograms of CO2 per hectoliter of beer. It's basically a 5-pound CO2 bottle that we're not releasing to the atmosphere for every barrel of beer we're making. It's a very significant savings on carbon footprint. Some misconceptions about mash filters. Mash filter needs to be hammer milled. That's not true. You can achieve a fine grist with a properly configured roller mill. In fact, most of mash filter beer made in the United States is milled with a 6-roller mill. We currently use a 2-roller mill where we offset the roller speed to get high shear. People say you can't flavor match in a lauter ton. That's not true. Coors, for example, Golden, Colorado uses a mash filter. They produce the same product in other plants around the world, no problem. Squeezing grains will extract tannins. In 30 years of brewing, I actually had somebody walk off a tour once, and it was a homebrew group, and there's somebody in the group who had actually brewed commercially for a couple of years, and he told me that you can't squeeze grains, the beer is going to taste terrible. Well, proper water chemistry is the key here. Proper pH control limits polyphenol extraction. And proper pH control will make bad beer, whether it's on a lauter ton or a mash filter. So having your process down is very important, but you can definitely make good light, crisp, clean beer. Nobody's had a Husky Heineken probably here. And like I said, Coors Light's actually made in a mash filter. So, saying it's going to be husky and harsh and astringent, definitely not true with good brewing practices. So what do we propose for this? We actually have designed a 20 hectoliter mash filter, which is about 17 US barrels. It's sized to produce 3 batches in about 8-hour shift. Allows us to make about 50 barrels per shift. We can actually make 3 of the same beer and fill 1 tank, or 3 completely separate brews. No problem. In this photo here, the tank on the right is a hot liquor tank. Our mash cooker is the second vessel. The kettle has the tall stack on it there. And we have a whirlpool behind that. And right in front here is the mash filter. We also do make a small version of this concept as well. Here is a 5 hectoliter. It's about a 4.2 US barrel system. We typically, this system right here actually has no hot liquor tank. This shares a hot liquor tank with a larger brew house. This is a pilot brewery in an existing facility. And no separate whirlpool. So production's a little bit more limited with this. We can turn 2 batches in about 6.5 to 7 hours. So if you want to do 10 hectoliters of beer or 2 5 hectoliter batches in a shift, very achievable in this situation. This system can also be configured a bit differently, up to about 7.5 hectoliters. A little bit less automation, definitely more affordable, lower volume though. So we'll compare what we found looking at the other brew houses. Conventional system, 4 or 5 brews in 24 hours is not uncommon. With a mash filter, that can be as high as 12 to 15 in 24. A lot of scalability here. Efficiency, extraction, 75 to 90 on a traditional lauter tun, 95+%. The advantage here is reduced grain consumption. Mash agitation kind of depends what you're looking at. There are people that are doing separate mash cookers on smaller systems as well. But a lot of systems do not have the ability to do stepped temperature mash, which restricts the speed of your conversion and the amount of extract that you can get. Water savings, very significant, about half the water usage. Milling, we do want to be a bit finer here. Not a problem to do that with a roller mill. We sell a mill that's configured for high shear. We run the rollers at different speeds, so we actually produce a bit more fines. That gives us really good extraction and also allows us to do quicker conversion as well. And our systems are configured to do pretty quick boiling. We have lots of steam jacket. We tend to see a 12 to 15% evaporation rate in an hour. So it's not uncommon for our customers to run a 45-minute boil and still achieve the same result. It allows us to move the beer on to the next step, to our whirlpool vessel, so we can actually move the next beer through, so we can get that second and third turn in that 8-hour shift. We do a lot on the control side too. We use PID control valves. It gives us really precise control. We tend not to overshoot mash temperatures. We can automate mash steps and things like that. We take a lot of the simpler tests away from the brewer. By no means is it a fully automated brew house, but timers and PID controls, step mashes, those are kind of small tests that we do take away from the brewer to focus on beer and quality. It's all touchscreen driven on the larger systems. The small system you saw, the 5 hectoliter, that's not as automated, but we do use PID temperature controls there as well. So how does this look on a schedule? Typically you'll see in our system, we can start a brew pretty much about every 2 hours. I think we can actually go a little bit more aggressively on this. This chart is showing a mash filtered brew on a high efficiency brew system. About every 2 hours and 15 minutes, we can definitely get that down to 2 hours. So number of brews per day and scalability, we definitely have advantages. We're even a bit faster than a 4-vessel brew house. Benefits of a mash filter over a lauter tun, we can summarize that. Higher efficiency. Mash filter can extract more sugars than mash. Higher brew house efficiency. Higher brew house yield in the same amount of grain. Faster processing time. We can extract sugars more quickly. We can shorten the brewing process a bit and increase throughput. Sustainability, we definitely have advantages on the amount of grain that we use, drier spent grains that can be stored for longer periods of time without starting to degrade. So you can actually have your forward pickup once a week instead of things starting to stink the next day. Water use is significantly less as well. The photo here is a 5 hectoliter mash filter in upstate New York. They have 5 and 10 hectoliter tanks. They've got a lot of flexibility, and this is a brew pub with limited distribution and nice tap room, so it's a good scale for them. So, about our company, we've been providing equipment to the brewing industry for a bit over 30 years. We specialize in supplying keg processing machines, flash pasteurizers, brew houses, and all sorts of other process and packaging systems to beverage industries, not just beer. Our team has 200 years of combined experience in designing manufacturing equipment. Our company headquarters are based in California. And we try to have a philosophy of bringing some really cool technology that brings efficiency to smaller craft breweries. And, as costs increase, these things are definitely flash pasteurizers, deaerators, carbonation equipment, brew houses, process control systems, cleaning systems, yeast propagation as well. Lots of other good things. So thank you. I'll be happy to take any questions anybody has. I did go a little quick there. I apologize. It's always kind of hard to tell where you are when you have any contact other than looking at your slides. So any questions? Comments? All right, I'll give this another minute or so. Any comments? I'll wait for. And all right, my contact information is here on the slide. This presentation will be available on YouTube in the next day or so. Andrew will take care of that. I'd like to thank Andrew and Craft Brew Professionals for having me here today. And feel free to reach out with any questions with my contact information on the last slide. Thank you.